Hello guys, how are you? Welcome to Cosmic Essence Education. My name is Maitray and in this video we'll be covering exponential functions. So let's get started. Alright, so exponential functions are a type of functions. Let's define them. I'm defining a function y which is equal to a to the power x, where a is positive, a is not equal to 1 and x belongs to the set of real numbers. Now, y is equal to a to the power x is the definition of an exponential function, but these conditions are also very important. They play a very vital role because it means that the base of the function a cannot be negative because of this condition. It cannot be equal to 0 and it cannot be equal to 1 also. So let's see why that is. Now, we want to define the exponential functions for the set of real numbers. Okay, because of that we have to eliminate a being a negative number or 0 or 1. Why? Let's see. Suppose a is equal to minus 1. Say I take a as minus 1, which is negative, and I take x is equal to 1 upon 2. In that case, y will be equal to minus 1 to the power 1 upon 2, which is root minus 1. Now we know that root minus 1 is not a real number. This is actually iota, which is a complex number and an imaginary number. So, since we want the range only to be real numbers, because we are talking about real functions. What real functions mean are functions in which domain and codomain both are subsets of real numbers. What is happening here? Y is coming out to be a complex number. That's why we want to eliminate those cases which make this a problem, and that's why we do not take a as negative. Let's move to why a is not taken to be equal to 0. We do not include 0. So suppose a is equal to 0 and I say x is equal to minus 1, then y is equal to 0 to the power minus 1, which is 1 upon 0, which is in fact not defined. So again this is causing us a problem and we do not take this to be in our domain. Now why is a not equal to 1? So let's see what happens when a is equal to 1. If I take a is equal to 1, y is equal to 1 to the power x, which is always 1 for any real number, here. So y is always 1. This becomes a constant function and it does not stay an exponential function anymore. That's why we remove these values from the base, because it will make the function not defined for all real numbers. That's why to keep the function defined for all real numbers, we put these conditions. So let's look at the graph. Okay, first we see the domain and the range. Now, domain is of course the set of real numbers. Range of an exponential function is always positive. For example, say if I take f5 to the power a positive number, it will always stay positive, obviously. But suppose if I take f5 to the power minus 2, so a positive number 2 raised to the power to a negative number, this will also be always positive. That's why the range of an exponential function is always positive, greater than 0. Let's look at the graph. Now, there will be two different graphs for the exponential function. depending upon the value of the base. Why? Because if a is greater than 1, so let's take an example. If a is greater than 1, let's say it is 2, and I increase the value of the exponent. Say if I am taking 2 to the power 1, then 2 to the power 2, then 2 to the power 3, then 2 to the power 4, the value of the function is increasing. Now, since the graph of the exponential function whenever base is greater than 1 is an increasing function, the graph of an exponential function is like this with y-intercept 1. Let's look at how we got this graph. As x tends towards infinity, y is equal to a to the power infinity. Now since a is greater than 1, a to the power infinity will tend towards infinity, so y tends to infinity. As x tends towards minus infinity, y is equal to a to the power minus infinity, which is equal to 1 upon a to the power infinity. This is equal to 1 upon infinity, so this tends towards 0. So as x tends towards infinity, y tends towards infinity. As x tends towards minus infinity, y tends towards 0 from above, that means 0 plus. So this is the graph we get when a is greater than 1. Now the second case is when the base is between 0 and 1, that means it is greater than 0 and less than 1. So when the base is between 0 and 1, suppose it is 1 by 2, let's see what is happening. If I increase the exponent, we see that the value of the function is decreasing. 1 by 2 to the power 1 is greater than 1 by 2 to the power 2, which is 1 by 4, which is greater than 1 by 2 to the power 3, which is 1 by 8. So as I increase the value of x, the value of y is decreasing. So this is a decreasing function whenever the base is between 0 and 1. Now this is the graph that we get for exponential function when a is between 0 and 1. Let's see how we get this. As x tends towards infinity, y is equal to a to the power infinity. Now since it is a decreasing function here, a to the power infinity will tend towards 0. As x tends towards minus infinity, y is equal to a to the power minus infinity, which is equal to 1 upon a to the power infinity. So the denominator tends towards 0, that means y will tend towards infinity. That's why as x tends towards infinity, y goes like this towards 0, and as x tends towards minus infinity, y tends towards infinity. So we see that the x-axis is a horizontal asymptote for the exponential function. Okay guys, so we saw the exponential function in this video. I hope you liked the video. If you did, hit the like button and subscribe to our channel, and don't forget to tell your friends about our channel so that they can learn maths from us just like you guys are enjoying. Thank you.